Welcome everyone. Since we have a few minutes, I'll take questions if anybody has some before we begin. So the question is, will today's lecture go over the Newton-Pepys problem? No, that's not the plan for today. Good morning. Okay, quiet class this morning. That's okay. Should you be able to answer all of assignment 3 by this point? Yes. I think you know everything you need to know. There's one question that maybe is a little bit easier once you know about expected value, but that's just one way to do it. You can also do it with straight up probability. So at this point you have everything you need in order to do assignment 3. Okay. So last class we started talking about independence, so independent events, and different kinds of independence. So when you have more than 2 events, there's sort of 2 different kinds of events of independence. A sequence of events can be pairwise independent, so if you take any two of them, then that pair is independent. Or it can be mutually independent, meaning that if you take any subset of them, then the probability that every event in that subset occurs is just the product of the individual probabilities that they occur. So independence is incredibly useful when you have it. It's also a common source of mistakes when people assume independence and it's not actually there. So today we'll look at a couple of examples in which it's very useful, and these examples occur basically because you design things so that independence is there. All right. So the first two examples come from, let's say, manufacturing, but you can imagine that they have. You could state these in other ways that would come from that would apply to other kinds of things. So we're going to look at circuits. So circuits are what you think they are. You know, there's some wires that go into them. There's some logic inside of them, some gates inside of them, and then some wires come out. That, you know, this logic gates compute something based on the inputs they come in, and they output these things on some output wires. And we're going to look at two different kinds of circuits. The first one we'll look at are what's called sequential circuits. And maybe the easiest way to think about them is the following way. So they make a kind of pipeline where, you know, some input comes in, and that input is an input to some circuit C1. It has some logic gates, ands, ors, nots, and so on. And then that thing outputs, and it outputs directly into another circuit, C2, and that thing outputs directly into another circuit, C3, and this goes on for n levels. So the last circuit in this sequence is Cn, and then finally the output comes out. Okay, so input comes in over here, passes through C1, passes through C2, through C3, and so on, all the way up to Cn, and then the output comes out. Okay? I mean, you can think of this as let's say one way to view this, but you can also think of, instead of these circuits, these are, you know, this is like something in a real factory where people make things, and, you know, this C1 is actually a person who is maybe a welder, and then C2 is somebody who does grinding, and C3 is somebody who does another part of this manufacturing process. And what's, you know, the input is a piece of metal that gets passed along from one to the other. So there are lots of situations where this kind of thing shows up, this sort of pipelines. One sort of issue with these things is that if you give an input and you want a correct output, everything along the way has to do its job correctly. Okay. And, you know, in manufacturing, if these are people, they make mistakes. And if you think more really in terms of real circuits, when you make one of these things, so in a factory, when you make a circuit like this, there's a certain probability that there's a manufacturing defect. You know, there's a probability that there's a manufacturing defect in circuit 1, and there's a probability that there's a manufacturing defect in circuit 2, circuit 3, and so on, all the way up to circuit N. And if you think about this, you know, probabilistically, you can say, you know, for each I in 1 to N, EI is the event, the circuit I works correctly. Okay? And we'll assume that all the events E1, E2, and so on up to En are mutually independent. Okay. And for us, this is going to be an assumption in the problem. Okay. So maybe the assumption makes sense in some applications, maybe it doesn't in others, but this is what we're going to assume now. And what you're interested in is, well, you're interested in the circuit working or not working. So either it works or it doesn't. And so you want to know what's the probability that the circuit works. And well, for that, let's just, to make our lives easy and so that we have something to compare against later, let's just say for each I in 1 through N, the probability that circuit I works is just some number P. So actually maybe all these circuits are identical. That happens sometimes. There are some certain types of networks where actually at each stage it's exactly the same thing that gets done to the data, in which case the probability that this one works is the same as the probability that this one works, if you're thinking of maybe manufacturing defects happening. So, you know, probability that EI is equal to, for any I, the probability that the circuit CI works is equal to P. And now you say, okay, let's look at the probability that the whole circuit works. Okay. Well, what does that mean? Well, the whole circuit works when this works, and this works, and this works, and this works. So that's the probability of E1, meaning the first circuit works, and E2, and E3, and so on up to En. Okay. So that's the probability that the whole circuit works. How do we compute that? Well, we have in our problem statement, we have this assumption that E1 through En are mutually independent. And remember, the definition of mutual independence is that if I take any subset of the events, what's the probability that all of them occur? Well, it's just the product of the individual probabilities that they occur. That's just the definition of mutual independence. And in particular, if I take all these events, what's the probability that all of them occur? It's just their products of their individual probabilities. So it's the probability of E1 times the probability of E2 times so on times the probability of En. And that, so that's just P times P times P times P, P to the N. So the probability that this whole circuit works if each individual part works with probability p is only p to the n. So think if p is a half and n is 10, so each of these circuits fails with probability a half, and there's 10 of them, then the probability that the whole thing works is only 1 out of 1,024. So 1 over 2 to the 10. So not so good, right? So fairly reliable parts that work with probability, well, a half. I think that's reliable. It was certainly better than working with probability only 1 out of 1,024. If you put them together in this way, you get something that quickly becomes unreliable. Okay. And that's shouldn't be a big surprise. Is that in general, it's not a good idea to plan projects and things with many parts, where if one of the parts fails, the whole project fails. And in this case, the whole circuit fails. And there's other ways to think about this. Right? You don't have to think of all this being sequential. Just think of this as anything that has n parts, and if any single part fails, then the whole thing is no good. You get the same kind of thing happening. That well, then the probability that the whole thing works is just going to be the probability that every part works, which, if things are independent, gives you a product of these probabilities. And even if those things were fairly big to begin with, once you take the product of all of them, they start to get closer and closer to 0. All right. So not great. So this is not a good strategy. We'll mark that here. Not reliable. Okay. An alternative to this, sometimes, depending on what you're doing, are parallel circuits. And there, schematically, they look like this. So with parallel circuits, you'd build these things so that there's an input or an interface on one side, output on the other side, and these circuits, things don't pass through them in a sequentially like this. Instead, all the inputs, each input goes to each circuit, and as long as one of the circuits works, at least one of the circuits works, then some output will come out that's correct. Okay? And otherwise, sometimes these circuits, some of them might fail, but that's okay as long as one works. And so the only thing you have to worry about, the only time your circuit will not work, is when all of these things fail. Okay? So seems inherently more reliable, and in fact, but maybe wasteful in the sense that you have duplicate circuits that are all doing exactly the same job, even though it's maybe not necessary. It turns out that actually this happens all the time. So in the computer on your desk, it probably has some number of cores. And companies like Intel and AMD manufacture processors. They manufacture some that are 2-core, 4-core, 8-core. You can even get up to 16-core on some very high-end things. So you probably know that when if you bought a computer in the last 20 years, you know, the number of cores is something that that shows up. But what you may not know is that in many cases, the 4-core processor and the 2-core processor and maybe even the 8-core processor, they were all manufactured exactly the same way. So the VLSI now has gotten so good that on something that's the size of a circuit that fits in your motherboard now, so like a CPU that fits in your motherboard, it's sort of, that CPU is so big compared to the size of VLSI circuits that it's easy to fit 8 cores on one of those things. Problem is, you know, each core has billions of little, basically transistors in them, in it, and so each core kind of looks like one of these, that there's, you know, billions of things going on inside of it, and if any one of them breaks, then that core won't work. So that's not so good. On the other hand, if you have an 8-core, if you build one that has 8 cores in it, and well, once they come out of the factory, these things get tested, and the tester realizes, oh, some of these cores don't work, and then what the tester does is disable them. So it just disables those cores, and you know, if you built an 8-core processor, it turns out that 6 of them work, but 2 of them don't, you can still sell that thing as a 4-core processor. And in fact, the only time that there's a complete waste is if you build an 8-core processor and all 8 of its cores don't work, then all you can do is bin it. So all you can do is throw it in the garbage. But everything else gives you something that's shippable, that you can sell to someone for some value. So this really happens all the time. Probably every serious computer chip that you buy nowadays has actually several copies of a fully working core inside of it, even if it's only sold as a single core processor. Okay, so same setup now. We're still going to do EI as the event the circuit I works correctly. We're still going to assume that the events E1 through En are mutually independent, and we're still going to assume that each one works correctly with probability P, and now we want to figure out what's the probability that the whole circuit works. Okay, so probability that the whole circuit works is E1, but now instead of and, it's or. E2 or, E3 or, and so on, En, right? If this circuit works, the whole thing works, or if this circuit works, the whole thing works, or if this circuit works, the whole thing works, or if this circuit works, the whole thing works. So instead of a conjunction, we have a disjunction of all these things. So that looks better. Now the problem is, well, we've said that these events are independent, and independence helps when you're taking conjunctions, but it does not help for disjunctions, right? So to compute a probability like this, we would have to use, if we want to do it directly, we would have to use the principle of inclusion-exclusion. And because we have n things, that means we get, if we do that, we're going to get a sum with nearly 2 to the n terms. So we need a more clever trick. And of course, the trick that we're going to use is the complement rule. So the complementary event to this works, or this works, or this works, or this works, or this works, is none of these work, right? The only time the whole circuit doesn't work is when all of these fail. Okay? So, so that's the complementary event, and we would like to know, okay, we know that if we can compute the probability of the complementary event, then we're good, and because the complement rule says we take 1 minus that. So in the set language, we can say that this probability is equal to 1 minus the probability of not E1, so circuit 1 doesn't work, and circuit 2 doesn't work, and circuit 3 doesn't work, and all the way up to circuit N doesn't work. This is a really common thing to do. You have an OR of a bunch of things like this, so much so that applying the principle of inclusion-exclusion is going to be hopeless because you have so many of them. Then it's usually better to look at the complementary event, and there the complementary event is going to be an AND of a whole bunch of things, which if you happen to have independence, that's going to make life easier. If you don't have independence, then you're still stuck on this side. But again, in this case, we assumed that the events E1, E2 up to En are mutually independent. And we said, although we didn't really talk about it for mutual independence, but certainly for normal pairwise independence, that if E1 and E2 are independent, then not E1 and not E2 are also independent. Okay, so that's what we have. And now we use that independence, mutual independence, to get the probability of not E1 times the probability of not E2 times, and so on, up to the probability of not En. What's the probability of not E1? Well, we can use the complement rule again. The probability of E1 is P. The probability of not E1 is 1 minus P. So this is 1 minus P, and so is this, and so is the next one, and so is the next one, and so on. So we get 1 minus P to the N. Okay. And now if we go with the same numbers, same numeric example we used here, if P was 1/2 and N is 10, this works 1 out of 1,024 times, so the probability of working is only about 1 out of 1,000 here. If we do the same thing here, well, if P is 1/2, this is also 1/2. 1 minus P is also 1/2. So this is 1 out of 1,024, and the complement of that is 1,023 out of 1,024. So on this side, we get 1,023 out of 1,024. And on this side, we get 1 out of 1,024. Okay, that's for P equals 1/2, N equals 10. So very close to 1 over here, very close to 0 over here. And actually, in practice, what happens is at very many scales, people combine these two things. So, you know, there's certain, for a circuit, even a really non-trivial circuit to work, a whole bunch of things have to work. Okay, and if there's so many of those things that it just becomes too unlikely that they can all work, well, then some of those things you duplicate with parallel circuits like this to make them more likely to work. And then the probability that they will all work, goes up accordingly. So, these two things are often used together, and in manufacturing processes, this is the sort of games people play. These things cost more because they're duplicating stuff often for nothing, but these things, they're very reliable. These things cost less because they don't duplicate things, but they're very unreliable, and so you mix those till you get a good trade-off. How do you know whether the probability you're looking at is a disjunction? So disjunction just means an or of a bunch of things. And when we talk about events, right, does event A happen, or are you in A or B? That means you take the union of A and of A with B, right? So in the Venn diagram picture of this, A or B is any outcome that's in A or that is in B. So the sort of problem statement here tells us that for sequential circuits, they all have to work, so that's where you get the AND from. And for parallel circuits, only one of them has to work, which is the same thing as saying the first one works, or the second one works, or the third one works, and so on. Okay. All right, so that's a fairly easy but very useful example. And pay attention here, because it's a super useful trick when you have the probability of a disjunction of a bunch of events, an OR of a bunch of events. Usually then what you want to do is use the complement rule to turn it into a conjunction. And then hopefully the problem told you that you have, should hopefully told you that you have independence, or that there's some other reason that you can understand what this probability is. Like maybe actually once you do this, you realize that this thing is maybe zero because the set is empty. That's another possibility, but something that makes this easier to compute. Usually independence is the thing. All right. So next I want to talk about a really nice old classic algorithm that is very relevant. The motivation keeps changing over the years, but it's always been relevant. So I'll give you the modern motivation. Originally, the motivation was picking a random line from a file. Then around the same time or later, it was picking a random element from a singly linked list. And today, we'll think of it as picking a random value from a data stream. Okay, so here's the setting. Companies like Amazon and Google, basically anybody who's selling things online, anytime you go to their sites, and very often even when you go to other sites, those companies see what it is that you're doing. So if you go to Amazon and start browsing, they see every item that you click on, and when that happens, that's a piece of of data that they see that says Amazon user so and so clicked on Amazon item X, seems to be interested in it. they like to save some of this information, or at least use this information to advertise things to you that you're hopefully interested in. And the issue for them is not getting, not being able to collect all that data. It's all available. So, and it's more than even just when you click on things on Amazon. So, in many cases, when you go to different websites, Amazon still knows that you went to those sites. And when you browse their site, they get super detailed information about even like how long you looked at something, or whether your mouse hovered over something, you almost clicked on a link. They can get that kind of stuff too. So from Amazon's point of view, the problem actually is not that they don't, that they want more data about you. It's that they actually have too much data. So they cannot store all of these things that happen for every user who visits Amazon. So this would just fill up data centers everywhere, and even if they could store it all, they wouldn't be able to process it all to do anything useful with it. So what they want instead is they want some sampling of the data. So they have this data stream, items come in constantly, and they would like to get a sample, a general picture of what's happening, maybe with all of their users globally, or maybe some individuals or groups of users. And so what they really need is a way to randomly sample data from data streams, from all these streams that come in. So, if you think of it in a very simplified way, then they've got on some server that's handling this stuff. You can think of it as some, there's some loop while the stream has more data, you say, well, grab that piece of data. Let's say S is equal to S dot next data. And what they want is, at the end of this stream, whatever that means. So maybe they say that their streams end every day, or their stream ends every 5 minutes or every hour. What they would like is, of all the data that came in on that stream, they want to get one item, a sample from that stream that's just one item that's equally likely to be any of the things that occurred on that stream. So that means if at the end of the day there were n data items, then I would like it that for any particular data item, the probability that I pick it is 1 over n. So if we get n data items, and let's call them x1 through xn. So these are somehow the values of x as you go through this this loop n times. The probability that we pick xi should be 1 over n. That's what we want. So n data items come in one at a time. At the end of this process, we output a random sample, and the probability that our random sample happens to be xi is 1 over n. And that's true for any I. Then our random sample really is uniform random sample. Everybody's equally likely to be picked. Problem is the following. We don't know n in advance. Okay. So I don't know before I start. Maybe my stream is going to be, I observe the thing for 5 minutes. Before I start, I don't know how many pieces of data, how many users are going to click things in the next 5 minutes. Okay. So I don't know the value of n in advance. If I did know the value of n in advance, it would be kind of easy. If I knew it, then I would just do something like this and say, let's say I is equal to 1. After I've seen this thing, I plus plus. So once this loop is over, now at this point n is equal to the value of I. Well, if I knew n in advance, I could do something like j is equal to a random integer in the range 1 up to n. And then here I would say if I is equal to j, then I save this thing. So I would say, I don't know, let's give it a name, z is equal to x. And then finally return z. So if I knew how many data items I was going to see, it would be easy. Before I start seeing them, I pick which one I'm going to keep, the index of the one that I'm going to keep, and then I start counting them. So I pick some number j between 1 and n that says I'm going to keep data item j. Then I start reading these data items and counting them, and once I see the one whose index I picked, I save it, and then I return it at the end. Okay. Well, so then the question is, this looks like it makes it hard. If I don't know n in advance, then how do I do that? Well, I can't. This doesn't work. So, can't do that. Can't test if I equals j. I need some other strategy. Still makes sense for me to count the data items as they come along, so that at least at the end I know the value of n, and at some point I should grab a data item and save it and return it. So z is going to be some random sample, but the question is, how do I decide if how do I decide which one to return? So think about this for a few seconds and think about whether this is even possible. Whether it's possible without knowing n in advance, whether I can actually really get a random sample where each thing occurs with probability 1 over n. I'm allowed to use random numbers, that's fine, but how do I use them if I don't know the value of n in advance? And while you think about that, I'll just mention the classic examples, other examples where this happens is, you have a linked list, a singly linked list, you don't know its length, and you want to pick one of its nodes at random, and you would like to traverse the list only once, right? You could traverse the list once to compute its length, then pick an index and go through a second time to grab this thing, but that takes twice as long as if you only have to traverse the list once. And the really old example is you're reading lines from a file, and the same thing. You want to pick a random line, but you don't know the number of lines when you start, and you don't want to have to read the whole file twice. Maybe it's a really big file. Both of those are nice examples, but they're really just about speed, trying to make something maybe twice as fast, whereas this example is about something that you really can't do. Like, for some data streams, you just simply cannot store the whole stream. No memory is fast enough to even capture it all. And so all you can do is, you're really stuck in this setting. Okay. So there's a couple of obvious cases. So one thing is, since I don't know the value of n in advance, it could be that n is really small. Like, it could be that n is 1, in which case I had better return something, right? So in particular, when I read the first data item, right? So I'm reading a data stream. It starts with some number x, called x1, and at this point, when I read this number, I don't know if there's even an x2. So that suggests that I have to save x1. So I should store it because there's a chance that it might be the only thing that I could do, in which if you ask me for a random sample from a one-element set, it has to be that one element. Okay? So that's one extreme. Somehow when you start, you'd better save this first element you see, at least temporarily. And the other, which is really a generalization of this, is if I have been going for a while, and now I'm looking at the ith thing, it could be that there's nothing else. There's nothing coming after this. Right? I don't know yet. I just saw the ith thing. I don't know if the stream has ended yet. So it could be that nothing is coming after. And if that happens, that means that the number of items in the stream, if you stop here, so stop, then that means the number of items in the stream is equal to I. So that actually tells me that if that happens, this last item should be returned with probability 1 over I. Right? Everything should be returned with probability 1 over n, so if n equals I, this should be returned with probability 1 over I. And so that means that when I see this item, before I move on to the next one, I had better save this thing with probability at least 1 over I. Because if I don't save it, I can't return it. And if I save it with probability less than 1 over I, then the probability that I return it is also less than 1 over I, which is not going to work if the stream ends right now. And if you think about this, this kind of means that actually we don't really have any choice about what to do. I want to save this thing, we could stop at any moment after the item that you've seen, and so I better save this thing, and I better save it with probability at least 1 over I. So let's do something like k is equal to random int in 1 up to I, and then if k is equal to 1, then say z is equal to x. Okay. So let's think about that for a minute. The first time we go through this loop, I is equal to 1. We get the next piece of data. We pick a random integer in the range 1 to 1, so we pick 1. And if the integer we picked is equal to 1, then we save it in this variable z. So the first time we go through this loop, this always happens. So x1 always gets saved in the variable z. And then we go through the loop again, and the second time we go through, x2, right, the second time we go through, when we pick this integer, it's either a 1 or a 2. The probability that it's equal to 1 is a half. And in that case, half the time we will save the element x2, and the third time, with probability a third, we'll save the element x3, and so on. And then at the end, we return whatever element we happen to have saved. Okay? All right. So, and we can actually check, well, we kind of believe that this works. If this is my whole data stream, only one item, then yeah, this works because first time through I save it, and then there's no second time through and I return it. That's good. And if the data stream stops right here, right after I see xi, well, so I go through this I minus 1 times, and then the ith time through, I'm picking a random integer in the range 1 through I. If that integer is 1, then I save xi and return it. So in that case, we can kind of see actually the probability that you return this thing, probability that we pick xi is 1 over I, and if we stop there, 1 over I is 1 over n, so that's good for that one. But what about the probability that we pick each of these things? That we don't really know yet. So just to highlight, let's put here, we'll call this thing star, and we say that this executes with probability 1 over I. So the ith time through the loop, it executes with probability 1 over I. All right. So now I'm going to claim that this algorithm returns a value z, which is equally likely to be any of the n data items that are in my data stream, even though I didn't know n in advance. So let's see if that's true. So the claim is for any I in 1 up to n, the probability that the algorithm outputs xi is 1 over n. All right. So how does that happen? Well, let's look at how the algorithm outputs, or what could make the algorithm output xi. So the algorithm runs for a while, and then finally during the ith iteration it sees the value xi. Okay. Now if it's going to output the value xi at the end of this thing, then this line here better execute during the ith iteration. Okay. So if you want to output it, you better save it. And that doesn't guarantee that you will output it, because something might overwrite it later, but it's absolutely necessary that you save this thing. So you must save xi, and that means that you have to execute that line. And we know the probability that that happens is 1 over I. But that's not enough, because now, if I'm going to output xi, I better not change this. So at this point, if this happens, then I'll have z equal to xi, but during any of the next iterations, I might overwrite the value of z, and then I won't output xi. So that means for each of these things here, I must not execute that line star anymore. So I have to go through this thing, save it, save xi, and then never save anything else. And then at the end, if that happens, if I did save this one and I didn't save any of these, then the value of z at the end is xi, and I'll output it. So I need to know what's the probability that that happens. All right, so for that, I mean, it seems that the critical thing here is, when does this line execute and when does it not execute? So let's say for each I and 1 up to n, we let ei be the event, line star executes on iteration I. And so that, from what we just said here, that means the event, the algorithm outputs xi. That means ei has to happen. We have to see xi and save it in the variable z. Right there. Ei happens, and none of those events, ei plus 1, ei plus 2, up to ei plus n happen. We save it in z, and we never overwrite it again. Okay. So, that means the probability that algorithm outputs xi, that's going to be the probability of this. Okay. And while now we have a conjunction of a bunch of events, we better hope that they're independent. Are they? Well, that depends on this random integer, random number generator here. But if it's a good one, or we can assume that it's a good one, then, you know, the integer that I generate when I execute it the first time should be completely independent of the integer that I get when I execute it the second time, that I get when I execute it the third time, and so on. And in fact, the whole sequence of integers that I get when I execute it these n times should be an independent sequence, so that the things in there should be independent, which means we should get the events E1 through En, if this is a good random number generator, should be mutually independent. So we'll assume that. In fact, this is usually where mutual independence comes from, at least in computer science when we do algorithms. We get the mutual independence because we use a good random number generator that, well, technically it can't guarantee that. It does so for all practical purposes. Okay. So, so that means that this product of all of these things, the conjunction of all of these things, is just this product of the individual probabilities. So that says this is the probability of EI times the probability of not EI plus 1 times the probability of not EI plus 2, and so on. Not probability of not En. Okay. All right, so let's chug through this. What's the probability of EI? Well, that we decided already is 1 over I. That's the first thing here. Now, what about this thing? So the probability of EI plus 1 is 1 over I plus 1. But we want the complement of that thing. So we don't want event I plus, we don't want EI plus 1, we want the complement. So we get 1 minus that. And here we get 1 minus 1 over I plus 2, and so on. And we'll put in the last 2 here. We'll get 1 minus 1 over n minus 1, and then the last one is 1 minus 1 over n. So that's that one, and this one is the term that you don't see there. All right. So I'm going to claim that, well, obviously, this equals 1 over n. Okay. Is that obvious to everyone? Probably not. Certainly wouldn't even be obvious to me unless I'd done this before. So let's see why this is equal to 1 over n. And for that, we should write these things in a more convenient way. So we'll keep our 1 over I here. Now, this 1 is just I plus 1 over I plus 1, right? So we write this out really longhand. I'll see I plus 1 over I plus 1 minus 1 over I plus 1. 1 is just I plus 1 over I plus 1. And then this is the other part of it. So hopefully you see that. But now we have a common denominator, so let's use that. So that's the same thing. All I did was use the fact that we have a common denominator to put that there. All right, but now I have a plus 1 and a minus 1, so of course I can just I can just get rid of that. And so on top, I'm only left with an I. All right. So that tidies up nicely. What about the next one? Well, there we're going to make this thing, we'll call this I plus 2 over I plus 2. Minus 1 over I plus 2. Now again, we have two things that have a common denominator, so let's just use that. And here I have a plus 2 and a minus 1, so that's just a plus 1. So that's what happens here. And if I do that to the next one, I don't think it's a stretch now to see that I'm going to get an I plus 3 on the bottom and an I plus 2 on top. Right. And I keep going like this, and at the end, for the last two, I will get a n minus 1 on the bottom, and n minus 2 on top. Here I get a n on the bottom, and an n minus 1 on top. Okay. And now, something absolutely remarkable happens. We have the product of all these things. So here I see an I on the bottom and an I on top. So those cancel out. Here I see an I plus 1 on the bottom and an I plus 1 on top. So those cancel out. I plus 2 on the bottom, I plus 2 on top. Those cancel out. In the next term, which is hidden in these dots, there would be an I plus 3 on top, so that cancels this one out. And that goes right through down here. There's an n minus 2 in the bottom just before this. That cancels this out. Then finally we have the n minus 1 down here, n minus 1 up there. So if we step back to all that and see what's left, everything cancels out except for the 1 on top and the n on the bottom. So, no matter which value of I you're asking me about, what is the probability that the algorithm outputs xi? Well, we just compute it exactly this way, and we realize it doesn't depend on I. It's 1 over n. It doesn't matter what value of I you've picked. Okay? Which is kind of remarkable, actually, right? So if you thought, until you do this, you could never believe that this algorithm treats the first thing it sees, x1, the same way that it treats the last thing it sees, or anything in between, right? You would for sure you would guess something. I mean, you might make some guess based on intuition that, okay, it's more likely to output x1 because it always saves it, or maybe you think ahead a little further and say, well, I know that it outputs xn with probability 1 over n, so the other ones must be, before that must be wrong. But no, actually it outputs every particular element with exactly the same probability. The probability is 1 over n. So it gives you a perfectly uniform sample from a data stream that it does not know the size of when it starts. And it only needs to store one data item at a time in order to do this. So there's no big buffer storing a bunch of data items and then picking one at random from the buffer. It only needs to store one at a time. So beautiful classic algorithm that actually seems to be getting more and more, it only gets more relevant somehow. Right, initially it was really about speed, and now it's really about doing things that actually wouldn't be possible. So there's not another way to do this. Saving the entire data stream is not an option. So really clever use of randomization and a gorgeous analysis. Okay. So there's a sort of part of this course that I sometimes skip, but maybe because of actually some of the questions today, I'll just mention briefly at the end. So there's a whole little section in the book about describing events by logical propositions. Okay, and I see actually, maybe from two of the questions asked today, that maybe that's confusing. So, right, if I say A or B, so does the event A happen or the event B happen? That in sort of formal and set language, that means A union B. So is the outcome so you're in A union B if the outcome is in A or the outcome is in B. So that's how these things are related. A and B is A intersected with B, right? So the set A intersect B contains a particular outcome if that outcome is in A and that outcome is also in B. This is the definition of intersection. Here's one that you may not have realized. A implies B. So what does that mean? A implies B. That means whenever A happens, B happens. So that means that every outcome that is in A is also an outcome in B, which means A is a subset of B. So in plain language or logic language, that this statement, event A implies event B, that means A is a subset of B. Let me just check on a couple more so I don't forget them. Oh, yeah. Yeah, no, that's the, I mean, the other one is, in logic you say not A, so the event A doesn't happen. That's just the complement of A over here in the set theory world. And the complement, remember, is you take the whole sample space, all the possible outcomes, and you take away everything in it. All right, so or means union, and means intersection, implies means subset of, and not means the same thing, complement. Okay? So if you get stuck, you can keep those in mind. And another thing which I've sort of stopped teaching because it's kind of boring, but I'll just put the statement on. We've used it already today, which is the sort of, we've used it twice already today. If A1 through AN are mutually independent events, then the probability of A1 and A2 and A3 and AN is just the product of the probabilities. And the more complicated one is the probability of A1 or A2 or A3 or up to AN is just 1 minus the probability of A1 times 1 minus the probability of A2 times, and so on, 1 minus the probability of AN. Okay? So this one we used always. So the probability of the conjunction is just the product. And this one, when we were doing the parallel circuit, this is what we used, right? The probability that if the first one works, or the second one works, or the third one works, is 1 minus the probability that the first one doesn't work times the probability that the second one doesn't work times the probability that the third one doesn't work, and so on. So they're not, I mean, there's nothing new there, and they're maybe only worth writing down because often when people apply this one, they forget the 1 minuses somewhere. So you can forget some people forget to do the 1 minus in each individual thing here. More common is they get too caught up in their reasoning and forget that whatever this probability is, in order to get this thing, they need to take 1 minus the entire thing. So be careful if you're using this, because it's easy to forget, just because things, you know, as you get more and more involved on these little sub-problems, like computing these individual probabilities, you're seeing all of the individual trees and you forget about the forest, which is what you're actually computing is the complement of the real thing that you want. Okay, so that's a good place to stop for today. If you would like, you can ask me questions for the next couple of minutes, or go out and enjoy the lovely weather outside, which I intend to do. It'd be nice to get out of this basement. Okay, so an old question here was, I don't understand why it executes with probability 1 over I. So remember, k was picked to be a random integer from the set 1 up to I. And that line executes if k is equal to 1. Okay. So there's I different choices for k. Each one gets picked with probability 1 over I. And so the probability that k is equal to 1 in particular is just 1 over I. Is this enough for doing assignment 3? Yes, you have everything that you need in order to do assignment 3. There's one question on there that I find a little bit easier to do if one thinks in terms of computing an expected value, which we'll cover, I think, next class, but it's not necessary at all. You have everything that you need to do assignment 3. All right, so thank you for showing up, and I will see you on Wednesday.